Okay, so this is the OpenAI. This is ACM AI's gym environment slash RL competition kickoff for winter 2020. So to start off with, we're going to talk about the gym environment and also do a Kahoot. Okay, I'll send you the link to the Kahoot post. Yeah, so just like join the link or something like that. Let me share audio. Okay, can everyone hear it? Okay, by the way, I didn't make this Kahoot. Alvin did, so I don't know what any of the questions are. How do I turn down the volume? Let's turn down the volume. Wait, I don't know. Oh, wait, I haven't got it. Okay, there we go. I fixed it. Synchronize the volume. Oh my god. Oh, this is classy music. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. If no one else is gonna join, then I guess I can just start. Okay.
Join later.
Okay, I'll start then. Quiz. What does a policy do in RL? Can I click on these? Wait, am I allowed to? Oh.
You're not right.
Oh. Okay, Stone's in the lead. But I don't think that's actually Stone though. What is Q learning? Oh yeah, so if you make top 3, we give you a Kahoot ring. Okay, POG, a method of finding the optimal policy when we don't know it. Who is this person? What does a Markovian transition model tell you? Okay, I kind of see how I'll do this now. What could happen before we're actually moving? So it's like basically it's like a Markov chain, where it just basically tells you that like, oh, based on this current state, these are the next kind of transitions we can go from this state, kind of thing. Dang, Stone has this high streak. What is an action in RL? I can tell that I'm the people. This is actually going to be a really tight competition, actually, not gonna lie. Okay, golf is in the lead right now. Alvin made them. What chooses your next state given the action you decided? Yeah, I think that's right. Yeah. Damn, golf is in the lead. Oh, it's two choices. Oh, read this question carefully. This is normal ML. I don't know what Alvin means by normal ML, but like, I think he has something in mind. But yeah, because it's normal ML. So technically, the normal ML, as in like supervised or unsupervised learning, there's no directly, there's no environment or agent. So I mean, technically, the agent. I mean, if you consider the network the agent, then it doesn't interact with the environment. It just like interacts with provided data. It's kind of different. Wait, so nothing happened.
Everyone top like a
Okay, good job. Everyone got it right. Who is this? Is it golf? I feel like it's gonna be golf. But yeah. Good job, golf. Wait, hi Kia. I think this is Catherine. Oh no. Okay, so that was the Kahoot. And this question was the agent interacts. This is kind of just like a trick question that Alvin made. So if you have problems about it, you can blame Alvin for that question. Okay, so just like a recap of what we talked about last time, we talked about state, which is basically a description of the agent in the environment, such as like location, speed, and that kind of stuff for like the current location and that quote unquote state of the agent. The next one is going to be action, which is just like a means for your agent to change the state of the environment by acting upon it, such as using the example from before, it's kind of like turning left or speeding up. These type of things will change the location and also speed, which is like technically like the state of such agent. And then the next one is reward. And reward is the value our agent tries to maximize. So there's actually in RL, there's like two main types that I think we're going to focus on later workshops, which is policy optimization and also Q learning. So the main difference between these two is that in policy optimization, RL algorithms, they only determine how good the current state is relative to other states, while in Q learning, it's actually going to be state plus action. So it's basically how good your current state is and also how good your current action is. So I think the easiest example of like a Q learning application would be something like you don't want to like move like too much in any direction. So it kind of like penalizes for moving a lot, even though like the state might not be that good, or you might be really good. However, for now purposes, we're going to just be working on like policy optimization algorithms, which is to define how good the current state is without actually considering the action that was taken. And of course, agent is the player in the environment, and the environment itself is kind of like the world where the agent is interacting with. So it kind of like chooses the next state based on the actions the agent takes. And I guess an example of this would be like a simulation of a car plus a world, or it can just be like a pendulum or something like that. And just to recap, this is kind of just like a diagram of what's going on. So let's say you have this agent, which is this thingy, and it takes some action AT, and then the environment basically outputs a reward in a state, which the agent will evaluate and use to predict kind of its next action. That was like kind of taken from last time's slide. So I guess we can just do like an easy example of this happening using tic-tac-toe. So for tic-tac-toe, the current state would just be an empty board because, well, there's nothing in here. And then the action is going to be, since we're O, our action just be putting an O here or like wherever. That's our action. The reward is going to be how well or how good that our current position or placement is. And then this is not like an RL thing, but this is just to keep track of the past kind of iterations. So just take note that in RL, it's a training per state action reward pair. It's not training using previous steps. So that's like the main difference. So for the first one, we decided to put an O in the top right corner. Yeah, top right, yeah. And then we get a reward of 1 because like, well, this move is like pretty good. Well, I think this move is like a really good move to do in tic-tac-toe. I always do this in tic-tac-toe. So the steps is 0 in top right with reward 1. So kind of like imagine that this is being fed into our neural network or whatever. Is it actually suboptimal? I thought it was like optimal position. The reward is assigned per step. No, because if you do center, then they can just because if you get 3 out of that, what, really? I thought it was the side. Yeah, okay. So addressing David's question, reward is assigned per iteration. So or like per step. So for each, basically it's basically the flow is like let's say your agent, you given a current state, your agent does something, and then your agent does something which is action, and the environment will decide on the reward and state, which is like fed into the model, which basically just changes the agent a little bit. And this is like done like per step kind of thing, because it's evaluating, because yeah, it's evaluating per state. Where did I say that? Yeah, this is evaluating per state and not like the overall how well it does. Because if it only assigned the reward at the end, then it would just be only kind of considering the end state, which isn't that good because we need to figure out the best path to that end state. So kind of think of it like more of like a greedy algorithm in the sense that it tries to take the best action at every state kind of thing. Reward? Yeah, a reward is just arbitrary because I didn't actually calculate how good these moves are, but I'm pretty sure this is like the best move.
Wait, I was wrong. It's one.
Haha, it seems I am the TikTok master. Okay, and then because kind of pretend that we're playing against the bot, so the bot decides to play this one, and then we play this position, and then yeah, 0 in bottom left. This is also a good move, I think. I'm pretty sure this is a good move. So this gives us a 1, and the current state just becomes, this should be 3 positions played. No, this is 2 positions played because we played, these 2 positions have already been played, and this is the new position that you play. And so yeah, these are the steps that have been taken, and this is the reward. So kind of think of it like something like this. So after this step, after this reward, this is fed back into our model, and this model, well, this is like more along the deep learning perspective in the sense that you're basically optimizing your network per reward and also kind of like state action reward pair in that sense. So it's basically optimizing per step, state, yeah, step. And then 4 positions played, which is these 4. Yeah, these 4 positions. And then you play this one, which is also supposed to be a good move. And then turns out you do a bad move, so you get a 0. Yeah, because you can technically win here if you just did this or this, but you decided to do this, so it's not like a really optimal move in that current state. If it was like some other state, like let's say you do it here and you play the 0. Oh yeah, that would have been the best move actually. I didn't realize that. Oh no, it's not because yeah. So yeah, if you did this move here, this would be the best move, but this is like a pretty good move also. So the enemy bot is just like an arbitrary bot in that sense, because we're training on kind of the user itself. Like we want to improve the users, how well the user is playing against the bot. So the bot is kind of like an arbitrary thing. So we can just kind of think of the bot as playing like random moves at all times. I mean, technically, if you had the bot play against the user, that would just be like a 2-agent system, which I think is also possible. That's covered more in depth in 150B. I'm not particularly sure what the 2-agent system is called. Yeah. But I think that's covered in the next lecture. Or Catherine, do you remember what the two-agent system is called? I forgot what it's called. I think it's like some sort of like actor-critic thing. Because one system is playing against the other one. But yeah, I think it's 2-player 0-sum. Yeah. Okay, and then next one, 6 decisions played. And since you, wait a minute, I just realized you won here. So this is actually a good move. Okay, yeah. I didn't realize that you just won here. It's fine. Yeah, so you basically won here. So this should be like a good move because, well, I mean, you won, so you get a 2. So basically what this kind of like the TLDR here is that it's kind of awkward, but it's fine. So with this like really simple environment, what the agent kind of learns is that given what the enemy or the bot is doing, like let's say he's playing this one, then the next position, like if we play this one, this would be like a really good, I guess, action to take in response to these current states, the previous states. And this is like occurs for multiple different iterations. And I guess since this environment's like pretty simple, I don't think there's that many different possibilities. I think it's like 2 to the, it's not like a really large number because it's like a discrete number. It's like discrete positions, and also there's only 9 positions. And there's only like 1, 2, 3, 4, 5, 6. It's like each player takes like 4 steps. So it's like really short games. So I guess technically your agent can just like learn every single possibility for tic-tac-toe and then just determine the most optimal kind of position for each of these instances of tic-tac-toe. Yeah, I didn't realize that this was a win. Well, that's kind of awkward. But it's fine. You get 2 wins then. So this is like a really good segue into OpenAI Gym, which is basically just a collection of many environments for teaching RL agents. And it's ranging from stuff that's like walking, like robot walking, to playing games like Pong and Pinball. So this is like and what makes OpenAI Gym really special in that sense is that it has a really constant format for ease of use. It's kind of, I think it's like likened to like ImageNet or whatever data sets are used as a standard in computer vision, because this is by like basically standardizing these formats using OpenAI Gym. A lot of papers can just like compare the results really easily. And then there's 4 main categories, which is classic control, algorithmic, Atari, and 2D and 3D games. So classic control is like problems like cart pull, pendulum, robot car following, car tracking, and that kind of stuff. Like classical, basically like physics problems. And I think algorithmic is like problems more related to, I guess, math and that kind of stuff. Yeah. And then Atari is basically just like your standard like Pong, Pinball, Space Invader. Yeah, those are pretty good, cool games. And then there's like 2D and 3D robots. These are, if you want to actually explore OpenAI Gym, these are most likely behind a paywall because of Mujoko's like a company or something like that. So if you actually want to like play around with it, you probably should email them and get like a student license or something. I got a student license but never used it. It's kind of awkward. And also, what makes this really good, this format, is that you can make your own environments, which we have done, and that'll be the basis of our competition. And then there's like a standard format for gym environments. So this is a standard format. So the first thing you want is the init function, which basically initializes action observation spaces and initializes any environment related variables. So this can be something like the current position, speed, and that kind of stuff. And you need action and observation spaces specifically for just like the deep learning applications that use OpenAI Gym, in the sense that you need upper and lower bounds for whatever actions it can take, and also upper and lower bounds on the observations that it can take. And that's basically just for normalizing the outputs, in the sense that because neural networks just do really well between 1 and -1. So if everything's between 1 and -1, then yeah, then your models are pogging off. And the next step is just the step function. And what the step function does, it takes, so every time we call the step function, it quote unquote takes one step based on the input action and then updates the state of agents. And what's really cool is that the outputs are observation, reward, and done. And what done is it basically determines whether the current state is at, I guess, a done, which can be something like, oh, reaching a goal, or somehow like reaching a goal or finishing a game or something like that. So that's what done is. Basically, what this is basically telling the model is that it'll always continue running until it hits done. And as soon as it hits done, it just stops stepping in the function, and then it calls the reset function, which basically just resets environments to initial values for the next iteration. And the kind of optional one is called the render function, which just visualizes the agent in the environment. So it's pretty intuitive to make these environments. You just need these things and then just like a lot of like folder management and that kind of stuff. And you got it. But the most difficult part is actually like getting your environment to work like really well. Because took me a really long time and it's still not working like pretty well. But we can address that later. So training and testing, this is more along the lines of how, or like an explanation as to like a previous slide. It explains it in more in depth. So basically at training time, the agent steps through the environment by determining the next step using observations from the previous step. And then there can be many episodes of training. Usually what I've seen is the RL algorithms trained for like a really long time, like 10K, just because it has to like run through the environment like 10,000 times or something like that. Just because, well, training is hard and there's a lot of different variables and things that can happen. So you need to train for a long time. And then the next one is episode. So basically this is defining episode. Episode is defined as going from like initial to done. And there can be like many steps per episode. So for each of these steps, it actually just trains. So like reward for each step is saved and used to optimize agent's future step if it encounters same state again. Um, there's kind of like, I guess for different algorithms, you would associate the reward observation and also the state per iteration, but training wise, it's probably more optimal to just optimize after you collect a bunch of them instead of optimizing per each one, because necessarily we don't know whether the specific step you take is good yet until you have like a lot of different, I guess, steps for that specific state, and then you can kind of determine which one is the most optimal. And you have to like consider that the most optimal for one certain instance is not the most optimal for another one. Because, well, I mean, since it's like a greedy algorithm, that's the main issue. And then the next one is just basically testing. So with testing, your agent just steps through the environment by determining next step using observations. And then we generally just use like one episode to see how well the agent is doing, or average of many, because sometimes for a lot of these environments, it it randomizes some different parameters, and in order to kind of like get a really good evaluation of how well your environment's performing, you should probably average it. And of course, the reward is safe but not used. So kind of like the reward is probably used to determine how well your agent is doing. And so challenge kickoff, and then special thanks to Jigen, Stone, Jason, Catherine for helping make this gym environment. It took a pretty long time. I'm tired. Okay, so OpenAI gym. So this is a custom gym environment to practice your bot on. The motivation is that let's pretend you're a golfer and you want to hit your ball to a target location in the least amount of steps possible. We set this least amount of steps to 10, and it should not take 10 steps to do it, because 10, your reward is going to be kind of bad. So the lesser amount of steps you take, the better. And the observations that we make are that for current position, it could be between 0 and 1250. And 1250 is the maximum number of units. Well, I guess kind of like the size of the map, if you want to think of it like that. And current height is like the lowest height and tallest height at the end of each step. So let me just draw that out. I think that's kind of difficult to explain. So let's say you have this is your environment, and this is your golf ball. And then, so, like, let's say this is your hip. And it doesn't really consider this height, it only considers this height, which is gonna be the same as this height for, well, I'll talk about that later, but yeah, so for that purpose, the height would just be 0. But let's say the environment's something like that, and you hit your golf ball like this, then your height would just be like somewhere here. But then the max height is this one, and the lowest height is this one. And there's gonna be wind. So what makes wind really unique is the sense that wind is a random value between -5 and 5 that will affect your agent. So it's not a purely physics problem that you'll be solving because, I mean, I don't think there's a really good physics solution to it, depending on how I implemented wind. But basically, what wind does is that let's say your environment's like kind of like this, and you hit your ball really high. But then wind is like going that way, and it's like pretty fast. So your ball would just go like that. Like without wind, it would probably do something like this. Oh no, that's wrong color. So without wind, your golf ball is probably gonna do something like this. But because of wind, your thing just goes like that. So your model will have to like somehow account for this. I don't know how, but it will. So good luck. And then action is velocity, which is 0 to 70, and also different golf clubs. So each golf club has like a different angle of trajectory. So think of this as like just a simple projectile motion problem where this determines a different angle that you could launch it in, and this is like the different amounts of power. And then reward, which is basically just how well it's doing. The reward is like pretty simple for this one, which is basically just 1 minus distance over target distance minus penalty, where target distance is going to be 1250, and distance is just, well, this value. And then we need to add this penalty just to punish you for taking many steps. Yeah. So this is how you make it so that it takes the least amount of steps. So there's 2 different stages for this competition. Oh yeah. So a little bit about this. This is a continuous. Both of these are continuous in the sense of how we implemented them. But for golf club is technically supposed to be discrete because you only get values of 0, 1, 2, 3. But how we did it was that we just made it such that if you get something like 0.5, it rounds to like the nearest number or something like that. It's like 0.5 rounds to 1. And that becomes your golf club, which is going to be 1. So it's technically supposed to be discrete, but we changed it into continuous just because OpenAI Gym doesn't like continuous plus discrete values. But everything else is continuous. So there's 2 different stages. The first one is the easy one, which is just a straight line. You hit your ball and tries to get there. It's like something like this. And yeah, then you win because you got to the last spot. But then there's this curvy function, which is kind of harder. You're like, I don't know, like that or something. This is like a pretty hard one, especially because for this last one, your end position is at like a downslope. So what makes this especially hard is that, well, let me clear this. Yeah, I haven't been able to necessarily figure out how to do this one either myself, which is kind of bad, but I will figure this out later. Which is that, you see, like if you're here or something like that, you need a specific angle such that it hits this exact position. Because if you don't, you're gonna get something like that. It just goes out of bounds. And especially, and because it's like on a downhill where like the derivative is like pretty high, so then this is gonna be like a really steep angle. And steep angles aren't really good because, well, the steeper it is, the more affected by wind your function is. So yeah, that's kind of also the benefit of wind because then you can get some like curve back kind of action, which might be helpful. And so the goal is that your agent, given observations, outputs the best action it can take. And so you want to make an agent that works on the first environment just to like kind of show that it works. Yeah, the flag is placed at 1250. And this is all made using Turtle because I don't really know. I mean, I could technically use other ones, but I think Turtle is the most intuitive one. And you make an agent. environment that just like works in the first environment. It's probably like just like a baseline just to show that your agent works. And then after that, you can kind of work on the second one, which is much harder to do. And especially because this randomized win part that's on both environments. This is still a work in progress, but for now you can do the first environment part. And so the baseline you kind of want to compare off of is just using simple projectile motion to calculate angle and velocity. Note that this also has a little bit of wind to it. So pure projectile motion won't work especially well. I might be wrong, but I don't think it works for this one, at least how I implemented projectile motion. And this is the GitHub. I think it's in the chat. I'll just post it again. Oh, no, no. Yeah, let me just post it again. Yeah. And then, yeah. So in the GitHub, what you have is, let me pull it up. So in the GitHub, it's like pretty simple GitHub. This is like standard format for an OpenAI gym environment in the sense that you have the main Go folder and then init.py, which is just like nothing. And then imps. And this is like all your, this is actually like the implementation. This is the visualizer. Visualizer still need to change a little bit because this is the wrong thing. But the Gulf environment works well. It works now, so you can like try testing it and stuff like that. And you can, I mean, what makes this OpenAI gym environments really unique is that even though you can actually access all this information, it doesn't really help you in the sense that it doesn't give you like an advantage in making your model. Because like you can implement physics functions just fine, but actually solving the issue is going to be much harder because, well, because even though there's like 70, because I mean, you can get anything between 0 and 70 and then 3. So already here, that's like, I don't know, like 200, no? Like 280 possibilities or something like that, assuming integers. So there's like a lot of different possibilities, even with number of actions you can take, especially with like different wind also. So it's going to take a really long time to actually brute force it. So you can't brute force it. It's not recommended. And this is how I implemented wind. And so what this is basically like, oh, at higher altitudes, the effective wind is going to be increased. And at lower altitudes, the effective wind is going to be less. So this is kind of like kind of like forcing your agent to not always take the highest step, because in the highest step, or sometimes you can take the highest step in the sense that if you're like really high, you'll get affected by wind a lot, which could potentially make you go farther or make you go backwards. It's kind of like a risk reward kind of thing. And then of course there's agent.py. I'll update you. This is setup, which is basically just another thing you need for gym environments. And agent.py is like a naive agent, which I didn't train the agent, but this is like kind of like how you want your files to be formatted. So then the server can just like pick it up and then use it. This is like kind of just like a basic, really naive one agent. I don't really need to. So kind of like what you want your agent to have, however, is that we want it to have the step function and somehow initialize your network. This is really important in the sense that this goes well into the test agent file. We're going to be using something similar to test agent file to actually test your agent. So what it does is that your agent equals this. This kind of just like calls your agent file and loads your weights for your network. I mean, it's perfectly fine if your agent doesn't use neural networks. It could just be like math stuff. Yes, either way works. But what we want is just kind of like a zip folder that contains this. And this is basically just like 5 runs and then shows how well it's doing in those 5 runs. And so what's going on is that you have an agent that steps. And this is just to, this specific line is just to clip your actions such that they're in the bounds of, yeah, so they're just in the bounds of the environment variables. Yeah. And then, yeah, submission process. Submission will be open on January 20th, 2 days after today. And to submit a file, you just want a file that contains an agent.py that contains your stuff and anything that needs to be loaded, and then the network weights. And yeah. And then we will be basically evaluating it on this stage ourselves and just taking like the average of like 5 runs, and that'll just be like your score. And then this is like kind of a big example. This is really important to have in the sense that your agent basically just needs to have a step function where given observations, it's able to just output a tuple, which is going to just be the action that you want it to take, which is supposed to be like, yeah, which is just the velocity and the golf club. So yeah, that's basically everything. And then some RL algorithms that are pretty cool that you can try out on. Yeah, the curry function is fixed. But yeah, so even though the curry function is fixed, it's still like a pretty difficult problem because of like the randomized wind. So it's really hard to just like brute force it. Yeah. And there's something wrong with random. I tried random before, but I don't think it just works. And these are some other resources. Oh, I forgot to share this. Yeah, I should be posting the slides. Aha. Okay, I'll post the slides here. Yeah, so that's basically it right now. Does anyone have any questions or anything? I got here 4 minutes ago. Um, well, um, yeah, so we just like kicked off the competition. We just like explained how the competition works, and I guess just basically like a basic rundown of gym environments, which is like really important in RL. And this is all recorded, so you can just watch it later if you feel like it. Is there a maximum height on the map? Yeah. So I'm pretty sure I set the maximum height to be, yeah, maximum height is 230, and the minimum is like -185. And this is just because of what the function looks like. Do I have the function somewhere? I don't think I have the function. But this is the function. Um, yeah. Wait, no, this is not the function. This is the function. It's kind of whack function. 256 like Minecraft. Oh wait, true. Okay, I'll do that in later time. So just like a note, or just give up partway through and go back to watching action. Yeah, that is also the move. So basically just like a note, there might be some updates for this one, just to make some things work better and more smoothly. And I will message in the group chat if that is the case. Yeah. So do you guys have any other questions? Oh my, I am so tired. Okay, so I guess if no one has any questions, I can just like, how long does it take for each game to play out? Like a game as in like a training iteration or just like watching? Oh, training? I don't know. It can vary a lot depending on your model. Because we didn't like actually define what kind of model you can have. So you can go from anywhere from just like the physics, which is probably going to be like near instantaneous, to like models that actually take a really long time to train. Like training my model takes like a pretty long time. And that's probably just because it's like trained it for a long time, but it converges like much sooner though. Um, for these applications, if you see that your model is like converging at some reward, then you basically know that it's basically finished at that point. Yeah. Okay. Does anyone else have any questions? I'm not sure how long this wait, Stone, do you know how long this competition is going to run for? Oh, is there a checking code? Stone, is there a checking code? Stone leave? Oh no, he did leave. Oh crap. Wait, Bryce, what's the checking code? Oh, oh yeah, I don't think anyone knows the checking code. Is there a checking code? No. Wait, hold on, let me stop sharing screen. I feel like there is a checking code. Is today the 18th? Yeah. Oh, there is a checking code. Oh, this is kind of cool checking code actually. Hit the mark. Okay, let me just put checking code somewhere. There we go. There we go. Okay. Does anyone else have any other questions? This is not as informative as the prior ones because this is just more a segue into the competition itself. And I guess, well, I mean, gym environments are pretty important, though, not gonna lie, because that's like the main thing with, um, that's the main RL, just gym environments. Okay, does anyone else have any other questions? I also need to fix this because I didn't realize this is a winning state. But it's fine. Just pretend didn't win there. Okay. Well, so how's everyone's days? I'm not sure. Okay, if anyone doesn't have any questions, I think we can just finish here. Oh yeah, um, some GitHubs that are pretty cool to look at. This one is pretty cool. You just gotta figure out how to use it. It's pretty intuitive. Just like put the golf environment into this one, and then you can just run it. And then there's also a PPO. So this is just like some like cool environments that you can try out. I don't like this guys. I like this guys. Yeah, so just like what you can just do is just like plop this folder, plop the golf folder into this file, and then it just works. Oh shoot, yeah. Okay, yeah. So this is like a pretty cool PPO implementation. You can also try Eric Hughes. I think Eric Hughes was also really good. So you just like plop the folder, you just like clone this, plop the golf environment, this one, and then it works just fine. And there's also this one for GDPG. You just plop the code into this, and then it just works. That's like the beauty of gym environments. You can just like plop them in, and then it works. Kind of cool. And these are some other problems in RL. Yeah. I can put the links in the chat if you want. Oh no. This one, the only concern I have with this one is that this requires something called RL Saber. I'm not particularly sure what it is. I trained on, so basically for my testing, I'm training on GDPG, like using his GDPG and then modified it a little bit. His model is able to converge on the easy task for now. but it struggles with this difficult task because it doesn't converge at a really good point. So I still need to kind of figure out what's wrong. It can either be my environment or the model itself. But there's like a lot of different other RL algorithms I can try out that are, you're not restricted to just using these two. Like you can try out a lot of them and then just like play around with the hyperparameters or try to like implement like your own or something like that. It's really open. Oh no, it's good if it does converge because I should just show you the graphs in DDPG. You want the it's not yeah, that's going to share. You want the thing to converge. Like kind of like this, where at the start it's like super bad, and then after the order just becomes super good, which is like really good. Wait, this is reward. Yeah, well, no, but it converges at the point, which is the most important part. If it converge, then you can just use someone else's algorithm. I mean, technically, yeah. But at the same time, with different, I mean, if it converges, it doesn't necessarily mean that that is the most optimal position because it can be converging at, like, even in this example, if it converges at like this point or something like that, that doesn't necessarily mean that that's the best position. Let me share screen. Like, let's say it's converging somewhere like here. That's not like as good as converging here. So that kind of requires a lot of like just like using different algorithms and then just like experimenting with these algorithms to try to find the best one for this specific task, or just like making your own. Yeah. The main purpose is just like kind of just explore RL and different algorithms. And I guess in later workshops, they're probably going to explain like how to implement it, like a really baseline algorithm and that kind of stuff. But for this one, it's just like to demonstrate what an environment is. Yeah, this is the Windows background. We're here expanded. Also, I need to rep bitbyte. I need bitbytes. Bitbyte. I can just stop recording now.